Okay, hi guys. So in this video lecture, we'll be continuing on seeing with more of these important points, case by case. Okay, so let me start off with third case. So in this case, we have been given these compounds or these carbocations, and we are asked to compare the relative stability. So in this case, no hyperconjugation will take place, so we cannot compare on the basis of hyperconjugation, so we have to compare on the basis of plus I effect. So obviously, as we have seen in the video lectures when we were discussing the inductive effect, we saw that the inductive effect of all the three groups, all the three deuterium atoms would be greater than the hydrogen atoms, right? So, as it is having more number of neutrons in it, right? So this would be the relative order of stability. But if we talk about this case, when we have the substituted groups, one having CH3 and one having CD3. So in this case, let us compare the relative stability. So as you can see that as hyperconjugation structures are possible for both, but due to weak bonds for CH, it would have more tendency to take place in hyperconjugation more easily, right? So as we have, I'll just write the explanation that as CH bond is more weaker than CD3 bond, hence hyperconjugation easily takes place in CH3 than CD3. So this atom over here, this substituents over here, we have to compare the rate of hyperconjugation in order to determine the relative order of stability. So CH3 is more weaker bond, so it would easily take place. Easily hyperconjugation can take place in case of CH3 than CD3. So this would be the relative stability order. So let us delve into case 4. Okay. So case 4 is if sp2 carbon is present in 3-member ring, then the ring is unstable. So I will just write sp2 carbon in 3-member ring is unstable. Okay, so let us look into the examples of it, and I will shortly give you the reason why sp2 carbon in a 3-member ring is unstable. We have to compare the stability order for these three compounds, and finally this one. Okay, so I'll just give you the reason why actually sp2 carbon is unstable in 3-member ring. The reason is the sp2, if you look at the sp2 hybridization, then it would be a planar structure, and the angle between all the three carbon atoms in cyclopropane ring should be ideally 120 degree, but as this is a 3-member ring, the actual angles are only 60 degrees. So there is a strain on each carbon atom of 60 degrees, because it has to be 120, but now it is available angle is only 60, hence 60 degree strain is there for each carbon atom available in the cyclopropane ring, right? So hence this compound would be the least stable, and as you can and this would be the most stable, right? And so this would be the most stable. So what about the remaining two cyclopropane rings? So if you look at the number of alpha hydrogen for this compound, it is having only one alpha hydrogen, and for this compound it is also having only one alpha hydrogen. So the stability of both would be actually, sorry, by mistake I drew the same compound here and here. So actually I'll just place the double bond between this carbon atom and this carbon atom. So how many number of alpha hydrogen are there in this cyclopropane ring? So the number of alpha hydrogen is 2 plus 3. 5 alpha hydrogen are there in this compound, hence the stability of this would be greater than this. So the overall stability order is 2, 1, 3. Okay, so now we look into the case 5 regarding aryl and vinyl cations. Case 5, aryl and vinyl cations. Okay, so what is an aryl cation? Aryl cation is nothing but this is an aryl cation, means vinyl ring having a positive charge on one of the carbon atoms, and vinyl cation is this is a vinyl cation. This is aryl, this is vinyl. Okay, so what would be the relative order of stability? As you can see that plus charge in sp2 hybrid carbon is present in both the compounds, right? Both the carbocation are actually having sp2 hybridization only, and so how do we compare which of the two compounds is relatively unstable? Or you have to compare the which of the two compounds or carbocations are more stable than the other. So if you look at the two compounds, here we have only one pi bond, but here we have 3 pi bonds, right? So this will have more partial sp2 character, hence on more electronegative compound or the phenyl ring we have a positive charge, hence this would be more stable than this one. And on the contrary, if we took this example, then what would be more stable than this and this? So in this case we first look into resonance structures or resonating structures. So obviously first compound has more resonating structures than the second compound, or we consider that the second compound has no resonating structures, so hence first would be more stable than the second one. Okay, so and if we compare what would be more stable among these two, and this, obviously this is more stable. Why? Because this is sp2 hybridized and this is sp, all the carbon atoms are sp2 hybridized, and for this we have this carbon atom as sp2 hybridized, but the cumulative effect is more in this case, as more number of double bonds are present in this compound, hence this would be more stable. Okay, now let's quickly look at case number 6. Now here we have some structure like now we have to compare the stability between this and this. So how do we actually compare? So for this structure, if you draw the resonating structures, we will have something like sorry, and this can actually go into its resonating structure like something like this. Okay, and this can actually go into resonating structures like okay. So in this case, the number of covalent bonds are also increasing, and oxygen is also having more oxygen is having complete octet, right? So for this case, this cation would be more stable than this cation. Okay, so now let's have a look at, so let me again write down the reason for the case. So the reason is this has more covalent bond in its resonating structure, and also complete octet. Okay, so I hope you remember all the 4 rules which we talked about when we were comparing the relative stability of carbocations. That the 4 rules were means obviously more covalent bonds. These were the 4 rules we discussed when we were actually comparing the relative stability of resonating structures: more covalent bonds and complete octet on electronegative element, complete octet of electronegative element, or just like let me write it atom only. And third point was on more neutral charge than actually having charged on some species or some atoms in the compound. And fourth one was negative charge on electronegative elements or atoms. Okay, so using, I hope you remember all these 4 points, and using the same we are actually going to deal with our next example. So the next example would be how do we compare the relative stability order of this compound between this and this. So as you can see that both can actually, if you draw the resonating structure of these two, so if I draw the resonating structure for this, we would have something like this, and for this I would have something like this. So let us compare the stability of resonating structures, and with the same we can actually extrapolate it to compare the stability of the original cations, original carbocations. Okay, so both have more covalent bonds in the resonating structure. Complete octet of electronegative element is present in both the structures. No, both the structures are not neutral. Both the structures have positive charges on the electronegative element. So what is having more negative charge on electronegative element? So as you can see that positive charge on electronegative element, this would be more unstable than this compound, because nitrogen is less electronegative than oxygen, so it can bear a positive charge on it. But on the same hand, as oxygen is more electronegative than nitrogen, positive charge on oxygen seems to be more unstable, resulting in more stability of this resonating structure for this compound. Hence this is more stable than this compound. Okay, so this completes our this lecture, and in the next lecture we'll be doing some more practice on comparing the stability of compounds. Okay, thanks.